As we cannot be in the lab doing this experiment, I'm going to walk you through what you would have done in order to collect the data necessary to determine the number of moles of water per mole of salt in a hydrated compound. First of all, what is a hydrate? It's an ionic compound that when it crystallizes, it traps water in between the cations and anions. We're going to look first at copper sulfate pentahydrate. It's as a crystal, it's really beautiful and blue. The copper itself is in, if you think about your molecular geometry, it's in an octahedral field with waters around in 5 of the positions, and then one of the positions is a sulfate. So with this sample, I'm telling you up front that I know that for every 1 mole of copper sulfate, we're going to have 5 moles of water. So let's act as if we don't know. Let's collect the data we need, and then let's do the math to confirm that really is a 5. Okay, so I went in the lab real quick and did this for you guys. I'm going to took a simple, nice, dry, empty crucible. I got the cool looking one with a handle because I could. The mass of the empty crucible is showing here on the balance as 20.921. I then used our handy dandy tare button, tared it to 0, and added copper sulfate such that the mass of copper sulfate inside the crucible is 1.254 grams. I took that and I put it on a hot plate. Put the hot plate on medium at first, but then start ramping the temperature up. So when it's first on the hot plate, when you look at it, hopefully if you look really close, you can tell that it actually is crystalline. You see some big crystalline rocks in there if you look really close. And then after even just a little bit of heating, if you'll look around the perimeter, you'll start to see where it's whitening. The blue crystal is becoming white. Well, it's not even just becoming white, it's actually also becoming a powder. Because what's happening is you have those water molecules trapped within that lattice, held between the copper cations and sulfate anions. As you heat it, the water is going to go to the gas state. It's going to be vibrating like crazy, and it's basically going to vibrate to the point that it crashes its way out of the lattice. Well, that's going to make that crystal lattice and that beautiful geometry kind of fall apart, and it's become an amorphous solid, which we refer to pretty much as just a powder. So we continue heating this slowly, and you'll see more and more of that blue color disappear as the water inside the crystal lattice is being evaporated. So more and more of it's gone. Eventually we get to the point where some of the crystals are now these amorphous little rocks. They still have some blue color. So I jumped in with a spatula and started crushing that up really well as it continued to heat over another few minutes. And eventually that's going to get you here to this nice chalky white solid. At this point, it is anhydrous. I have driven all of the water out. So the only thing that should be in this crucible at this point are copper plus 2 cations and sulfate anions. So if we weigh that again, we let it cool first. We never put anything hot on our balance. We let it cool first. We take it back and we weigh the crucible with the anhydrous. The mass of those two together is 21.717. So just to be clear, now we have a different type of solid. And for this guy, if you look, this is SO4. This is SO4. This is SO4. This is SO4. Every single oxygen that you see in here, red oxygen, is due to the sulfate polyatomic anion. And then the other guy you're going to see is the copper cations, copper plus 2 cations. There is no water in the lattice at this point. So that's the difference between hydrated and anhydrous, is all the water has been evaporated out of the lattice. All right, now, so if you were in the lab, that's what you would have done. So now let's start using those numbers to actually do the math.